Hi guys, second video for today. This is a very interesting problem, and I thought I'd do another video on it. So I think my audio is pretty bad. There we go. Okay. So, let me go ahead and share my screen. So actually first I'll go through the problem. So this is kind of a variant of the daily from 2 days ago, I believe. It basically, given two integers n and k, you want to return the kth lexicographically smallest integer in the range from 1 to n. You can see the lexicographical order is like defined here, right? So 1, 1, 0, because 1, 2, right? Like it's lexicographical order. Hopefully that makes sense. In the interest of time, I'll just go ahead and share my screen and we can go ahead into the implementation. Or sorry, the explanation of the implementation, I should say. Okay. So the way we're gonna solve this is we need some efficient way. Oh, I'll walk you through what we did for the previous daily, right? So what we did is we essentially just counted every number for in a DFS fashion. So let's imagine we start from 1, right? And then we have multiple different endpoints from there, right? So we have 0, 1, 2, blah blah blah, 8 and 9, right? So let's say, and this is a huge tree, right? There's other nodes here and blah blah blah. Okay, so initially what we did is we just DFS to this tree, and that question wasn't for the case, it was just for every single possible one. So we just DFS'd, and this tree goes on forever and ever and ever and ever, basically covering every single number in existence, right? You can imagine if we split this, right? You can construct any possible number from this tree. So we're just going to DFS, and once we get to a point in the tree, so we go down here, and once we get to a point in the tree where it's outside the range of n, we just end. Okay, hopefully that makes sense. Let me erase this. So our solution essentially the key thing here is to see that this is something called a prefix tree, right? So imagine instead of numbers, these were letters. We could represent a letter like ape, like this, and we can represent apple, like this, right? So what this does is it makes it really easy for us to store strings in a efficient data structure, where we can see does the prefix AP exist? It's very simple. Does the prefix APE exist? It's very simple. We just iterate through, right? So that's the same thing we want to use here. We want to see if the numbers exist in this tree, and we want to basically what we want to do is find a way to intelligently traverse this entire tree. So one thing we can do is let's break this up into different subproblems, right? So one big subproblem that would make this entire thing a lot very, very easy for us is how many numbers are between, let's say in this tree, right? So let's say in 1, 0, and then we traverse to let's say 3, and then we have 0 and 1. All right. I want to be able to tell how many numbers in the range from 1, I'll just write the question. How many valid, which means it's in the range from 1 to n, are between two nodes in the tree? So basically, how many nodes are in this subtree? That was a terrible drawing, but how many nodes are in this subtree, right? And this is remarkably not that hard of a question. So I want you to think the lower bound of this is if we just go from 0, 0 on and on and on, right? So what we want to do is every time we traverse down a level, we're going to add how many of our numbers are in this level. So imagine we do the same thing here, right? We're just traversing, sorry, that was very messy. We're just traversing down as far as we can to the left, and this is going to be our J marker. So this is our upper bound. You know what? I'm just going to name this upper bound. Upper bound. And this is our lower bound. So what we can do is, so right now we're at 103, right? We're going to traverse down. So this is going to be our lower bound. Sorry, 103.1 is our 0 is our lower bound. Our upper bound, 1031 is our upper bound. So every time we traverse down the level, right? Obviously between the range from 1030 to 1031, let's make this left side inclusive. To here, and how many numbers are there? There's only one. So this is just obviously upper bound minus lower bound. Okay, pretty simple. And then once we traverse down, so this is the first iteration. Second, we're going to add 0 to the back and 0 to the back here. And how many numbers are between this? 10, right? So there's 10 between this, and so on and so forth until we reach a point where, let's say the upper bound in this case was 10,700. So let's say in the third iteration, we're going to obviously go above. And we're going to say 107, or sorry, I'm getting confused right now, but 103100. Okay, obviously this number is outside of this range. So we're going to end and not count and return the answer 11. Okay, and there's a kind of a nuance to this. What if the lower bound here is in the range but the upper bound isn't? So we're gonna update this, and this will be the minimum of UB. I'm just gonna call it upper bound, and n plus 1. Right, because so imagine our lower bound is 2, and our upper bound is 2. Or n is 2, right? We still want to count 2. You'll see in the implementation details why later. So we're going to say like n plus 1 in upper bound. Okay, pretty simple. So that's how we count how many numbers are in the subtree, right? So I'll draw a new tree. So 1, then 0, this. I'm not gonna draw the numbers anymore, guys, but you guys get the idea. Actually, you know what, to keep on doubting myself in terms of this, but yeah, sorry, my handwriting has definitely not gotten better over these videos. But yeah, so what we're gonna do is we're gonna traverse down the tree. We have two cases, right? So we get here, we don't want to count 1 because it has no neighbors yet. So what we're going to do is we are going to count 1. It does have neighbors technically. We're going to make this root like just the null string, which, if you take like a computing theory class, epsilon is the empty string. And so we're going to start at 1 because the range is from 1 to n. We're going to start from 1, and we're going to call the method we just described before as count nodes, and we're going to say n, 1, 2, like this is cur plus 1, and this is going to be equal to m. So we have two cases if m is greater than or equal to k. What does this mean, right? Or let's just say greater than. What does this mean, right? So this means there's more nodes in this subtree than we have to look for. So in this case, we're going to traverse into subtree. Else, that means it's not in the subtree, so we're going to iterate to neighbor. How do we traverse a subtree? It's just cur. We just multiply it by 10. We just add a 0, right? We just add a 0 to get to the, get into the subtree. Else we iterate into the neighbor. This is just cur plus 1. Okay, hopefully that makes sense. We have a really good outline now. And let's get into coding. Let me stop sharing my screen. Okay. Private, first let's implement the helper function. So int count nodes, int n is equal to, what am I doing? Int n, int lower bound, upper bound, and I want to get into the habit of making good docu-strings kind of, but they don't have autocomplete in this. No, it's this, yeah. Counts how many numbers between lower bound, numbers lexicographically between lower bounds and min, and this should be this, and n plus 1 upper bound. Okay, so we're going to initialize something called answer, and there's one key thing wrong with this code. It's great practice to understand, especially this. I highlighted the mistake, but we'll solve it at the end of the video. You'll see why. But yep, while the lower bound is inside the range, so while lower bound is less than or equal to n, we're gonna say, and then return answer. We're gonna say answer plus equals the minimum of n plus 1 upper bound. Just realized I made a mess up, but yeah, upper bound minus lower bound, and then we're gonna traverse down the tree to the left side by just multiplying by 10. Okay, that should work. Now we're gonna say int cur is equal to 1, and at the end we're just gonna return cur, which is our answer. We're also gonna say, because we've already counted 1 in terms of k, so we're gonna say k minus equals 1. Let's keep start indexes consistent, and we're gonna iterate while k is greater than 0. I think it's that. I believe it's that. But yeah. And now we're gonna say int m is equal to what? Int m is equal to count nodes over there. So let's see, int m is equal to count nodes of n. The lower bound, which is cur, and cur plus 1. And what were our two cases? We have if m is greater than k. Should that be? Yeah, if m is greater than k. What do we say in the thing? Yeah, m is greater than k. We're going, and then let's have our else statement. If m is greater than k, what do? We traverse into the subtree. So we traverse into the subtree by doing that, and we say k minus equals m. All right, sounds good, looks good to me. Or sorry, k minus equals 1, because we only skipped 1 node so far. Excuse me. But in the other case, we do cur. We skip the subtree, so we do cur plus equals 1, and we do k minus equals m. Okay, let's run this. We're gonna get an error. I set the test cases up for that. Oh wow, okay. Well, we're gonna get an error once I submit this. It's because we're getting integer overflow error. Especially when you're coding in C++, you always have to look out for this. So what I'm gonna do, convert this to a long, convert this to a long, and then we have to cast this to a long. All right, let's use this. I'll run. work. Okay. Now we submit. And pretty good, guys. 100% runtime. Memory could be a little better. I'm assuming because of the calls we're making to this. Like, if you're not familiar with stack teardown and stuff, like, basically every time you call this function, you know, it's going to create, like, allocate a new stack and stuff. Assuming it's because of that. But, yeah, 0.2 MB. Probably because of that, but yeah. Maybe try implementing this yourself without the helper method. Your code will be a little messier, but maybe you really like being very memory efficient. I don't know. But thanks for watching, guys. And hopefully we'll do a video tomorrow. But yeah, see you guys.